probably hearing a message that says this meeting is being recorded. I don't get to hear that. Okay, so again, everything is set up in WebAssign, all the assignments. I will be asking you probably every week for some handwritten assignments, just to be sure that you're constructing solutions well, although I know from other courses that you're good at doing that. So I'm not too concerned and I don't have to get too extensive. I do have to emphasize, and I don't think I need to emphasize it to you, but I'll say it anyway, that make sure that when you do the assignments, you're doing them legitimately, read the text, look at the examples, and then dive into the assignments. Don't take shortcuts. However, I haven't seen any indication that you actually do that. Try to avoid it if possible. The points that you get on WebAssign are only maybe 20% of your grade, give or take 5%. The points that you get on tests are pretty much the rest of your grade. And make sure that you're focusing on what you need to learn in order to do well in the tests, as I assume you're going to do. Okay. The textbook, the ZIL textbook, I really like this textbook. I didn't like having to make a change from the textbook that I've been using. It's the textbook they use at Virginia Tech, but there's no WebAssign support for that text. So we're going to go to ZIL. And the more I see about ZIL, the better I like it. I like the other one quite well too. I use them interchangeably, but right now I don't see where one is better than the other. We'll see how it works out. The WebAssign assignments for this course are fairly rigorous, as you'll see, but I think you'll handle them just fine. So what I'm going to do at this point, if you don't have questions, and if you do, please enter them, or if you can get your audio to work, holler at me. I'm going to go section by section. I'm going to stay pretty close to the text here, since it's a text I haven't used before. And I've got some notes here, just notes on the topics, and I'll be going back and forth to those notes. But actually, I can put those notes up in chat, just so you see what I'm looking at. Okay, there are my notes. Don't know if you're going to want to follow those because they're pretty abbreviated. They're for me, they're not for you. The first note is, what's a differential equation and what is a solution? So I'm going to give you a couple examples of differential equations. Now, you've already seen differential equations, like the equation my double prime equals negative ky. It's the equation you solve for simple harmonic motion. And you know that that equation can be put in this form. And now you need a function whose second derivative is a multiple of itself and its sines and cosines to do that. So you would let y equal I'll use C1 because that's more consistent with the way your text does it. C1 cosine of square root of k over mt, where the derivative is understood to be derivative with respect to t. And that's one solution. Another solution could be C2 sine the square root of k over mt. And y in general equals C1 cosine of the square root of k over mt plus C2 sine of the square root of k over and that's off the screen. I'll pull this over a little bit. There we go. Okay. This is your general solution. You have two parameters. C1 and C2, so it's a two-parameter family. Of solutions. And given two conditions, you can fit the C1 and the C2 to those conditions and get a specific solution. Okay, so given you can find C1 and C2 to fit the conditions. Now, there might be conditions that wouldn't fit, but in general, for this situation, you can usually find solutions as long as you don't get ridiculous. Okay, you can find C1 and C2 to fit conditions, to fit those conditions. Example, if y of 0 equals 0 and y prime of 0 equals 1, then you can evaluate C1 and C2. Okay, y of 0 is just this because the sine of 0 is 0, and that equals 1. And that should be cosine of k over m times 0. And the cosine of 0 is 1, so C1 equals 1. Y prime of 0 is negative C1 square root of k over m sine of the square root of k over m t. Now you would also have the derivative of the sine, which would be the cosine, and that would be and t is 0. So that's just C2 square root of k over m. That has to equal 1. So C2 equals the square root of m over k. And your solution now is y of t equals cosine of the square root of k over m t plus square root of m over k sine square root of k over m t. That's pretty simple conditions, but you can do this in various ways. We're not going to get deeply into that right now. Just choose this example because it's one that you're familiar with. At least more familiar with at some point in your physics education. So there it is. Now, This illustrates several things. Again, this is a second order equation. You have a second derivative and a y. So solving the equation, you don't generally use integrals to solve these equations, although in some equations you can do that. But in solving the equation, you're essentially doing an integration, and you got to do two integrations because you've got a y double prime. It's like you have to integrate y, then integrate, or you got to integrate y double prime and then integrate y prime to get a solution. And you can kind of think of it that way, although you don't actually solve these equations by doing actual integrals. Each integral, though, would give you an arbitrary constant. So you can kind of understand the landscape in that way. Okay, well, okay, and I'm kind of monitoring the chat and probably ought to, don't know why that's highlighted, but chime into chat if you need to. Okay. Okay, so the main idea here, and let me look, what is a differential equation? What is a solution? This is an illustration. This is an equation. You're looking for the function y that solves the equation. That's the solution. In this case, right there is the solution. If you plug this solution in here, take two derivatives, multiply by m, and then take the function itself and multiply by negative k, you should get an identity. So you just plug the solution into the equation. That's how you test whether you have a solution or not. Okay. And I'm trying to keep myself on track here. So that's what a solution is. Okay. What's an ordinary differential equation? Well, you read that. It's an equation like this. What's a linear differential equation? Well, okay, let's go back to what's an ordinary differential equation because there's something I want to say about that. Okay, let's take this equation again. This equation is of the form y double prime equals negative k over my, or y double prime equals f of y where f of y is negative k over my. So any equation like this, any function of y you want to put in here gives you a differential equation. So I'll say any f of y gives us an ODE, ordinary differential equation. I'm not going to write out those words, you'll see them in the text. Any f of y gives us an ordinary differential equation. If f of y equals y squared minus e to the y, then y double prime equals f of y is y double prime equals y squared minus e to the y. Okay. If f is a linear function of y, then this is a linear equation. This is nonlinear, okay? We have a linear ordinary differential equation. And it has order 2 because the order of the equation is determined by the highest derivative, okay? You have a second derivative, that makes it order 2. Now, I'm looking for a place to put my foot here. Move these things over a little bit, and maybe I'll have one. Okay. So, Fy is linear. We have a linear ordinary differential equation of order 2. Okay. Now, we could have y double prime equals t squared plus 3y minus 5y prime. Actually, a fairly easy equation to solve, as we'll see later. Okay. Now, this is the form y double prime equals f of t, y, and y prime. Okay, your highest order term is equal to this function. This is a function of t, y, and y prime. Okay, this equation is linear. Since the y and y prime terms are linear, it doesn't matter that t is not linear. The linearity of an equation just requires that y prime, and y double prime, and any other derivatives of y have to be linear. Okay, you can't have a y squared, you can't have a y prime squared, you can't have a y double prime squared. If you have those, the equation's not linear. And sometimes you can solve those, but a lot of times those things are just completely intractable. Now, the general form is y, the nth derivative, whatever n is, this. Okay, where n is the highest derivative, and your function over here is a function of your variable, which in this case is t, since that's what I used before. A lot of times you'll see x, could be any variable, but a single variable here, and then your lower derivatives of y. An example. Okay, there's an example. Now this is order 4. and it's nonlinear because 1 over y isn't just a multiple of y. It isn't linear. Okay, well, there are a variety of other ways of writing these forms. We want to understand this notation and how it relates to what an equation might actually look like. And if you're going to solve this equation, you would bring all the y's onto one side and put all the t's on the other, if that's possible. You could also have coefficients of this equation that aren't constant numbers. Another example. Didn't leave myself room, so I'm going to have to spill over here. And lots of luck solving that one. Okay, this is still linear. With non-constant coefficients. Okay, this is linear, this is nonlinear, but you do have constant coefficients. Being nonlinear, whether the coefficients are constant or not, it's going to be screwed up. It's going to be hard to solve, usually. Okay, so that's classification of these things. Now let's see what the next topic is. The order of the equation, the f of x, y prime. Okay, yeah, the official form of an equation. Okay, this form could be written the official form would be, and your book uses f, I used f here. I'm going to use g for the function. This equals 0. And you would get this form simply by subtracting this side, subtracting all this from both sides to get a 0 over here. Okay. And that's very straightforward. Usually when you solve it, you're going to want to have your highest order derivative on this side and other stuff on this side. Not always, because if this side, well, not going to worry about that now. Okay, I could demonstrate that, and I'm tempted to, but I'm not going to. Okay, that's kind of the official form. The normal form is this. Okay, so it can be written in this form, but usually you're going to write it in what we call the normal form. That's just notation. It's not a big deal. I've talked about linearity. Okay, there's this thing called interval of definition. For example, I don't want to write out this whole equation, but let's just say you got a simple equation, y prime plus tangent of t times y equals t squared. This equation is not defined when the tangent of t is not defined. So your possible domain of definition might be the interval from negative pi over 2 to pi over 2. Or and I had less than or equal there because I just kind of wrote that, but it's less than because obviously t cannot be pi over 2. Tangent being sine over the cosine being 0 at any multiple of pi over 2 gives you an undefined value. And of course, you understand the graph of the tangent function. It has the vertical asymptotes at every multiple of pi over 2. That's it. Okay. Or you could have pi over 2 less than t less than 3 pi over 2. Or in general, n times pi over 2 less than t less than, now, getting careless there, n minus 1. I could have written it with an n plus 1 on this side, but boy, you can write it, okay? And this means that if you have a condition on this equation that says, let's say that y of pi over 4 equals 1 or whatever, that's a condition on y at pi over 4. That means since pi over 4 is in this interval, that any solution you get is only valid in this interval. Okay, if it was y of 7 pi over 4 equals 1. Okay, 7 pi over 4 is all the way around here on your unit circle, and that's between pi over 2. Between 3 pi over 2 and 5 pi over 2. Yeah, that was right, but somehow I didn't instantly visualize the 5 pi over 2. I wanted to go to 2 pi, but never mind. Just a brain freeze for a second. Okay, so that's what we mean by interval of definition. One example where you have an interval of definition that isn't the entire t-axis, the entire set of real numbers. Okay, if this is e to the t y and a t squared here, there's no problem. Those functions are both defined everywhere. So any solution you get would be valid for the entire set of real numbers, t any real number. Okay. We've got the idea of a solution curve. And of course, for our first example, where you had y equals cosine of t plus square root of m over k sine t. That's just a simple function of cosine and sine. You have to superpose the cosine and the sine waves, but you get a curve of some nature, depending on what the values of k and m are. So you plot that and you have a solution curve. I want to talk a little bit more about solution curves. I want to talk about the geometry of solutions. And this is something that Zill doesn't go into in this first chapter, but he does go into it quite heavily in the text. I'm going to have to set this one down. I don't have a usable back. Okay, I always think this is an important thing to see on the first day of the course. So we're moving along here, so I think I'm going to go ahead and do it. So let's just say we have y prime equals .4y plus t. Turns out this is a really easy equation to solve. See very soon how to solve it, but probably not just yet. We're going to wait till Zill says it's time to do it, because one thing I love about Zill is in his first chapter, he anticipates a whole lot of the rest of the course in a way that's very similar to the way I would do it. So the guy must be a genius. You know, how could anybody duplicate my thinking without being a genius, right? Well, ho ho. But I love the way he does it. Okay. Okay. Well, here's one thing he doesn't do quite in the first section, but he does it in the first chapter. I think I can be confused. In any case, he does quite a bit of it. Okay, so what we want to say is we've got this equation. Let's pretend we don't know how to solve it, because we don't right now. And we have the initial condition y of 0 equals 1. Just a very simple equation. Well, this means that your solution curve is going to have to go through the point 0, 1. Okay, so whatever your solution is, when t is 0, y has to be 1. So it has to go through the point 0, 1. If I had a different condition here, it would have to go through a different point. Okay, so solution goes through this point. This means that at this point, your solution curve has a property that its derivative is 0.4. Well, the derivative is the slope of the solution curve. The slope of the solution curve through the point 0, 1 is 0.4. Now, Zoom does have the somewhat noxious characteristic that it has a kind of a banner thing that shows you the time, the date and the time at which my profound words were conveyed to the unsuspecting public. And that's a little bit of a pain, because I like to, keep writing. And I think that this is going to get obliterated by that. So I'm just going to lift this up briefly. So anybody that really wants to see can pause and see what I've written. Okay, it's a fairly obvious idea. Okay, y prime is 0.4. So the slope of your solution curve has to have a slope of 0.4. Okay, so here we have I'm looking for notation and I don't have it. Slope is 0.4. So whatever your solution curve is doing, at this point, it's going to have a slope of 0.4. Okay. Now, if we follow this slope for little ways, for example, we follow this slope while t changes by 0.1. That's going to give us 0.04. Yeah, that'll work. Don't want this the result to be too small. The rise will be 0.04. And your run is your 0.1. So we end up at the point 0.1. .44. We've moved over 0.1 unit here, and we've moved up 0.04 units. So now we're at this is not a very accurate representation, but it isn't too bad. So now we're here. Okay, this point is not going to necessarily be on the solution curve, but it's going to be close. Okay, so assuming these functions are nicely behaved and don't do weird things in the interval from here to here. Okay, and we can make weird things a little more specific, but right now we're just going to understand that if a function isn't pretty pathological, if these functions are pretty pathological on this interval, then this little segment here is going to be pretty close to the solution curve. So I'm going to kind of color that segment blue and say that that segment is nearly a part of the solution curve. Okay. This point near the solution curve, kind of messed up that word curve there, but hopefully you can understand that. And this segment is near the solution curve. I don't know why I don't want to put the V in there because my R's look like V's, I guess. Okay. So there's a segment that's near the solution curve. Okay, well, we can do the same thing again. We can take this point, and that point is 0.1, 0.44. we can do the same thing again. And it's not the word I want. It's 0.1 times 0.44. Sorry. Got the wrong numbers. No, actually, I don't have the wrong numbers. Make sure I did this right over here. 0.4 times 1 is 0.4. But it's y that isn't 0.44. Okay, I've got something wrong over here. And it's not 0.44. And it's not 0.44 here. And it's too bad you don't have audio because you could have screamed at me because it's an obvious error. We end up at not 0.44 because this point is 0, 1. It's 1.04. In other words, we started with y value 1. We added 0.04. So it's 1.04. And this is going to be 1.04. And this is going to be 0.4. Okay, now, if we multiply this out, we get 0.416. We add that to 0.1, we get 0.516. And I apologize for screwing that up, but that's okay, 0.516. Okay, so we make another segment here. Slope is 0.516. It's somewhat steeper. I'm going to maybe exaggerate the steepness a little bit. Okay, now the slope is 0.516. If we go another tenth of a unit, then we're going to be out here where x is 0.2, t is 0.2, and we're going to be at some point on the curve. So if, and it's got right, if delta t is 0.1, then instead of rise, I'll just say delta y is 0.516 times 0.1, which is 0.0516. So the new y value is I don't really want to write y.2 there. New value is 1.04 plus 0.0516 equals 1.0916. And the new point is 0.2, 1.0916. And this point is still close to your solution curve, but not as close as before. So that every time you do this approximation, these points are going to get a little further from the solution curve. If you want a better solution curve, you can use a smaller interval. If you go to an interval of 0.01, it's going to stay close to the solution curve a lot longer. Okay, well, you can understand then that if we have the initial condition, and if we take the limit as this interval approaches 0 and do a whole lot of steps, approaching an infinite number of steps, we're going to get a solution curve. Okay, so if we refine this, okay, let's see. We can kind of see lots of tiny steps. And this is over kind of far. You can read it better if it's here. Just don't have a lot of lip here, but I think this will work. Lots of tiny steps lead to a good approximation of the solution curve. Okay, lots of tiny steps give you a good approximation of your solution curve. And the limit as tiny steps approach 0. You get the exact solution curve. Now, this is not a technique for solving the equation, but this gives you insight into how the solution develops. Since for the functions that we have here, 0.4y and t are both defined for all values of t, or at least t is defined for all values of t. It's not like you've got a tangent of t here. Then in the limit of tiny steps, your solution applies everywhere. Okay, so for this example, our reasoning implies our solution exists for all t. Okay, we can project the solution curve to all values of t everywhere in the plane. for all t from negative infinity to infinity. If the equation is y prime equals 0.4t plus the tangent of t, we can't project our solution beyond an interval from negative pi over 2 to pi over 2, because if we have that interval, let's say we get over here to pi over 2, and we try to do our solution from 1.5 to 1.6, pi over 2 being about 1.57, then we're crossing over a point where the slope approaches infinity. And all bets are off when that happens. Okay, well, that gives you a little more insight into why we have these intervals of definition, intervals of existence for solution. So that's going to come in handy. It's a pretty straightforward process. It's not hard to understand if you think about it. And this is actually the Euler method of approximate solutions. But it can be refined. You can do a predictor corrector method. You can do a higher order method, a Runge-Kutta method, where you approximate these things by quadratic curves, or higher order approximations. Okay, and that's very important stuff that we'll encounter a little bit later in the course. Okay. Your book gives an example. And I'm going to let you just read that example. I don't want to try to explain that at this point. And we can talk about it after you've worked the assignment. Trying to give you what you need to work the assignment. There are implicit solutions. You can see examples of that in your text. Solution of an nth order equation is an n parameter family, just like the solution of our first equation, y double prime, my double prime equals negative ky. Gave you a 2-parameter family of solution. If it was something times y triple prime and maybe some double primes and some primes and some y's in there and some t's, you would have a 3-parameter system. It's like you got to integrate 3 times to get your solution, although you don't actually do that. We'll see a lot about that later in the course. That's not going to be particularly important for the equations that we get early in the course. Something you want to store away, though. There's a terminology, a particular solution, and let me just explain that. Let's see. Not here. Okay, there it is. Your solution here is a specific solution. Okay, here's your specific solution. Actually, here it is. And you would call that a particular solution. You would call this your general solution. Just terminology, and not terminology that, in my experience, gives people any serious trouble when you actually need to use it. There are singular solutions, but I'm not going to address that right now. You can read about it. You have an n-parameter family of solutions. But there is another solution. Well, I'm addressing it, so I guess I am. There is a solution to this equation I guess it is in the family though, where y would equal 0. So all its derivatives are 0. And in this case, that would still be in your n parameter family, but sometimes a solution like y equals 0 can be a solution that doesn't lie in the family. Although any n parameter family could have all coefficients being 0. It's kind of analogous to the idea of singular matrices, linear independence, linear dependence, and so forth. Talk about that when it really comes up. One kind of neat thing that's probably worth looking at, if I can find a good board to use. There's probably one behind here. Yeah. Let's just say that you have two solutions to an equation. One solution being y equals x squared, and the other being y equals negative x squared, so that your general solution could be c1x squared minus c2x squared. Now that's really just an arbitrary multiple of x squared, so this is not a great example. But this could be a solution. This could be a solution. Also, you could have the following solution. Okay, this solution would be a piecewise defined solution. Okay, so this solution could be y equals negative x squared if x is less than 0, x squared if x is greater than or equal to 0. This might still be a valid solution to your equation. It's kind of a neat idea. You can read a little bit more about it in your book. Your book uses an x to the 4th instead of an x squared. But you're more familiar with the x squared graph than the x to the 4th graph. So that's what I use. Okay. Let's see, let's make sure we're still here. Yep, there we are. Okay. Okay, that's about it. I think I can turn you loose on the first section, and I think you're not going to have trouble with most of the problems in this section. A couple of the later problems might be a little bit challenging. If you have questions, of course, you can email me, or we can talk about them next time. Get a chance, read ahead in your book a little bit, just scan it, see what you're looking at, because you'll understand what I talk about next time a little better if you've kind of looked over section 2. I think the pace for this course, and let me go back over to WebAssign, assuming that WebAssign hasn't kicked me out. Boy, they don't give me much room here. I can email, I can log in pretty quickly. They've made login a little more cumbersome. You got to click more. And I hope they had a good reason for that, other than just trying to aggravate their clients. No, don't tell me that was wrong because I did it right. Oh, wait a minute. Yeah, I typed in the password right, but it was the wrong password. There we go. Now it tells me bad request. I've got a couple of minutes. I'll get into WebAssign eventually. Let's go back here, all the way back. No, actually, that's not good. I have to go back to the original login, but that's ridiculous. Now, what did it just do there? It didn't take me to the original login. It took me to, okay, I clicked on the wrong thing. Okay, well, actually, I'm going to stop the recording now because